we're going to start by talking about the atmosphere this week. So, when you look at the atmosphere and you go through it, it's interesting that the mixture of gases in the lower atmosphere, basically the area we're going to be in forever, up to 43 nautical miles. You're not going to be flying an aircraft that high unless you're going to be going into space. So the mixture is always the same. The ratio of oxygen, nitrogen, and other gases is always going to be the same. So it's interesting that if you go start at the surface or go out, you're always going to have that content. Now, as we go through this chapter here, interestingly, we talk about temperature as being one of the things. We're going to talk a lot more about temperature in a couple next chapter, but temperature is the kinetic energy or the motion of a molecule. So the more the molecules move, the warmer it is. The less the molecules, the colder it is. Absolute zero is a point at which all kinetic energy ceases. And since you can't have negative kinetic energy, you can't have negative anything below absolute zero. So if you think about it, there's always motion in those little molecules, random motion. So they're always moving. The faster they move, so the hotter the air is, the slower they move, the colder it is. So now that we have a small idea of how molecules impact one parameter of the weather, let's go to density. Okay, first thing you got to know with density and with the atmosphere is a fluid, but it's not like water. You ever try to compress water, you just really can't do it. Air can be compressed. We do it all the time when we pump air into a tire or remove air from a tire or other things like that. We compress air. So you have a certain number of molecules in a cube of air. If you have less molecules, the density is lower if the cube is the same. Say you expand that cube, keep the same number of molecules, again, the density is lower. Because the atmosphere is compressible, makes this a little more complicated than if you had just a nice bottle of water. Bottle of water would say, oh, the number of molecules is always going to be the same. But in the atmosphere, since we don't contain it out here, the number of molecules is going to vary depending on how big a volume we're talking about. And whether, think about it, the atmosphere, if everything's pressing down on it from above, it's going to be tighter compacted, smaller, more molecules in a smaller area. Density will be greater. The higher up in the atmosphere, the density is going to be less. So just a little something to think about. So pressure, just a real quick glimpse at it. Pressure is the force these molecules apply when they're moving around. So if I have a square cube that has a certain number of molecules, if I increase the temperature, guess what? And I don't allow that cube to change size, the molecules are going to be hitting the sides of that cube faster. There's going to be more air pressure. Now, if I increase the size of that cube, there's less air pressure. Well, guess what? Because the atmosphere is a nice compressible air, it means that when you have molecules moving faster, they're going to tend to spread out. When you have molecules moving slower, they're going to tend to be closer together. So density is going to literally fluctuate by how high the temperature is. And think about it, the atmosphere is really tiny compared to the whole Earth. So, and interestingly, 90% of the mass of the atmosphere is below 53,000 feet. However, you got to go all the way up to get the other 99.9%, 164,000 feet. Oh yeah, at 18,000 feet, half the mass is below that level, So you can see how the air has been compressed down. So there's a lot of more air down closer to the surface. Most layers in the atmosphere are defined by temperature. So we live in the troposphere. Most of your aircraft are going to fly either in the troposphere or the lower stratosphere. Stratosphere is where temperature begins to increase. So if I'm looking at a temperature curve, as I go up in the atmosphere and it constantly is decreasing, maybe fluctuating a little bit, I'm pretty much in the troposphere. All of a sudden, the temperature is going to start warming. I'm moving into the stratosphere. Guess what? The mesosphere, temperature starts cooling. Thermosphere, temperature starts warming. So it's interesting how we define our atmosphere in these layers based on temperature curve. We could talk about ozone concentration or other concentrations in them. Ozone is more concentrated in the stratosphere. That's where most of the ozone is. When we talk about a standard atmosphere, you hear this a lot in aviation terms. Well, how much is it deviating from the standard atmosphere, or what's the standard atmosphere? Basically is we take a calculation of temperature and we apply it to this pretty much to the troposphere. So temperature is going to decrease at a certain rate, and that is going to be your standard atmosphere. It's basically looking at a whole bunch of records to determine that. So the next chapter, we're going to get into more energy. Solar radiation is what drives all the energy in the atmosphere. So with that, we can bring in and move this energy around by radiation, conduction, or convection and advection. So let's start with solar. All right. The sun sits in the middle of everything. We rotate around the sun. And our Earth is tilted 23.5 degrees. So say I am in the middle of summertime. The sun, because of the tilt, will be more directly coming in to the northern hemisphere. With that, that means we are going to be getting more solar radiation, and all of a sudden you're going to heat up our area more, the northern hemisphere. Go to the opposite side. Oh, sun's tilted, our Earth is tilted away from the sun. All of a sudden we're going to get a whole lot more energy coming into the southern hemisphere, and the northern hemisphere is not getting as much. At the equinoxes, it's about equal. So literally where the sun directly is overhead varies by the season. Now, what I mean overhead, if you look straight up, if you could lay down on the ground and look straight up at noon, when the sun is directly over your head, you would either be, say if it was an equinox, you'd be at the equator. Anywhere else on the earth, that sun is going to be tilted slightly away from you. And it's based on latitude. If you think about it, at the equinox, if we're at 40 degrees latitude, the sun looks like it's at a 45-degree angle. If I'm at the North Pole, which is 90 degrees, or the South Pole, 90 degrees, it would look like it's at a 90-degree angle. 90-degree angle, man, I can't see it hardly. So this is a concept you've got to understand. There's an angle to the sun. It doesn't directly point. And if there's an angle, it means it covers a larger area. The greater the angle, the more the area of that solar radiation is spread out. We don't get as much. So here you can see, here is that angle. And here you can see the same time of year, and that sun is spread out over a much greater area. You're going to be calculating some of these angles and all in a couple things. I give you the equations. Here they are in the book. So How does the sun's energy get to us? Through radiation. Radiation is an electromagnetic wave that moves through things or from things. And because of that, it's a wave. It literally has a trough and a crest. And the distance between two crests is the wavelength. The radiation from the sun, electromagnetic radiation, moves at the speed of light. So when they're closer together, there's stronger radiation. Further apart, the radiation is less intense. And you can see here the sun's radiation. We can see most of it in the visible light spectrum where we look at it. However, the Earth is cooler, means Earth emits at a longer wavelength. The waves are further apart, so there's not as much energy that comes out of the Earth as compared to the sun. And naturally, nothing is simple on the atmosphere. Some of the atmosphere radiation is reflected from the atmosphere back into space. Some of it is absorbed by the atmosphere. Some of it comes in at angles out in a different way. Some of the Earth absorbs the sun's energy, as well as some of it reflects it. So all that makes up the whole amount of the sun's energy. But we're going to talk about the different processes in all this chapter. And then we have conduction. Think about conduction. Conduction is when if you put your hand on a burner, it's going to burn your hand. That's conduction. It's literally touching two surfaces that are a different temperature. And always energy flows from the hotter surface to the colder surface. So that's why you are heating up very quickly when you put your hand on something hot. Convection and advection. So they are, I think I'll just do it to show you something here. Here's the current observations weather map for West Virginia. Advection. We have temperatures plotted and wind. You're going to learn wind direction is the direction of the air is coming from. So if I am at Beckley, West Virginia, or Elkins, West Virginia here, Elkins has got northwest winds. So I'm at bringing the air from the northwest. Temperatures are relatively cool. Matter of fact, they're downright cold in parts of the mountain chain there. 61 at Beckley right now, for example. That air is being vectored to the southeast. So that means that those temperatures are being pulled that way. So that would be cold air advection. If I am looking upstream and I have colder air, I have typically cold air advection. If I'm down in my neck of the woods, southeast Virginia, and I look up to the northwest, I'm seeing temperatures in the 60s up in Pennsylvania. I am in the 70s, so what's happening? Cold air is coming my way. So that's cold air advection. So those are the topics we're talking about. Temperature is we've talked about it as being how fast the molecules are moving. So my molecules are moving faster in my area compared to what Beckley's are. And my temperature is being adjusted by cold air advection coming from areas like Beckley or Pennsylvania in this case. So when you're looking at a weather map, I want you to notice where the wind's coming from, and the temperatures are always on the upper left corner. So those two things can tell you whether it might be getting colder at your place or warmer at your place, depending on what's around you. Yes, mountains impact temperature. Think about it if you're higher up in the atmosphere. We've talked about the troposphere cooling with height. So the mountains in West Virginia are going to be colder than the lowlands in West Virginia. Just some of the things I wanted to set you up with this week. I hope you got a little bit out of that. Let me know if you have some questions.